focusing on fan-out solutions and also some of the technical promotion function.
We're now at SiP Global Summit， 我们现在位于系统及封测国际高峰论坛的现场。那么今天的专题讨论呢，将邀请到的是日月光半导体资深处长赵新华先生，以及 IBM Research 处长 Dr. Spike Naraya， 从完整的供应链的各个角度提出当下以及未来所面临的挑战，并在座谈当中适度的引导大家一起来讨论出解决方案。那么稍后呢，将由日月光半导体我们的赵处长赵处长呢，将率先的先带领大家来做主题的讨论，相信呢能够激荡起精彩的对谈。我们来看看现场的画面。
Although he is very young, he is also an expert in design, development, or process technology in EVG group. So let's give him a warm welcome for the presentation for us.
Okay, so hello everyone. It's an honor to be here today in this afternoon session to discuss about chip stacking in high volume manufacturing and moving into wafer level hybrid bonding. So in this presentation, I will first start with state-of-the-art technology that is being used in high volume manufacturing right now, review what specifications are achievable with that and what limitations those technologies have, and then take you on a journey to what is the most advanced technology we have at the moment. I will also point out on what areas we're working on. And then finally, at the end of the presentation, I will share some more innovative technology with you that is related to silicon photonics integration, putting compound semiconductor dies into 300mm silicon wafers, process flows that we think are high volume manufacturing capable for this type of technology and enable the industry to manufacture silicon photonics chips at a cost that is competitive and compatible with high volume manufacturing. So let's get started. So the first topic I will review is, okay, where do we stand today? I think it's a very famous device nowadays in the 3D community, so it's the hybrid memory cube from Micron. And this here shows a cross-section of the chip stack, and you can see here that in fact the interconnects that are in there are still very bulky. So they consume a lot of space in X and Y direction, but they also have a significant space consumption vertically in the Z direction. So if we, another problem with this technology actually is that it is also relatively complex to manufacture. So first of all, the chips that are being stacked here into the final cube have to be thinned before stacking. And this is done with a technology that we from an EVG perspective like, because it uses our equipment. But it's not really adding a lot of value other than enabling the handling of thin wafers. So there's temporary bonding technology where the product wafer is bonded on a carrier wafer to enable thinning of the product wafer and then backside processing of the thin device wafer to form the contact pads that are required for stacking. And then finally the wafer is released from the carrier, output on a dicing tape, is getting diced. So The dicing then results in thin singulated chips, as you can see up here. And those chips are individually stacked in a chip-to-chip fashion to form the memory cube. So it's a very complex process flow, relatively slow, and therefore it's an expensive device. So as we all know, these hybrid memory cubes are not in consumer electronics today, and that is for good reason. They are probably too expensive for that type of application. Another topic is, as I already pointed out on the very first slide, that the dimensions of the interconnects are, of course, a lot smaller than wire bonding and other things, but they're still relatively bulky as compared to the through-silicon vias, or relatively bulky as compared to the back-end of line layers. So this here shows an overview on the dimensions that are used by SK Hynix and Samsung in their memory stacks in the high bandwidth memory. So the TSV dimensions we can see already the single-digit micron number, so they are quite small. Aspect ratio probably around 10 to 1, because the chip thickness is in a range of 50 microns. And but the pitch is still relatively relaxed at 40 microns or 67 microns. And this is, as we can also see here from the interconnects, driven also by the large interconnects that are used to stack the chips. So what can we do about that? Here I'm borrowing some overview slides from that were originally developed by IMEC. I think they do a very good job in segmenting the individual interconnect technologies with respect to the application space, with respect to the densities they can provide. And the way they look at it is, okay, there is a 3D system in chip technology where the interconnects are done at the chip I/O level. So the memory cubes that we just looked at would fall exactly into this first category. And then as you dig further down into the chip, you could do the interconnects at the global wiring level, you could do the interconnects at intermediate wiring levels, and you could then dig even further down, and you eventually would be at the local wiring level. And the ultimate would be that you have two transistors on individual wafers manufactured, and the transistors connected between the layers. So the interconnect would be at the transistor level. Well, those three they categorize as a 3D system on chip. Talking, let's say, more conventional language, it has the performance benefits like a system on chip, can offer interconnect densities like a system on chip. And then, in the eyes of IMEC, the only real 3D IC would be if it's interconnected at the transistor level. That can also be translated into numbers. So at the global level, we find the typical dimensions that we already saw from the memory stack. If we talk about the global back-end of line level, then we would have a contact pitch in a range of 5 microns and maybe eventually moving to 1 micron with a relative density of 4 to 100 interconnects per square millimeter. And then in the intermediate level, we already today have smaller interconnects going out to 1.5 eventually. And then we would have to have interconnects at a contact pitch of less than 100 nanometers in order to match the leading edge semiconductor nodes that we have today. And now, from an equipment supply perspective, what's getting more interesting for us is how could the stacking be done for that? That's our business that we are in with EDG. And here, for the global, let's say, I/O level of the chip, as we already heard in the memory cube example, it's done based on a known good die basis, chip-to-chip assembling, or edge-based chip-to-wafer assembling. So it could be stacked on interposers. And then for the next 2 or 3 categories, at the global interconnect level of the chip, intermediate and local level of the chip. The bonding would be done at wafer level, most likely, because the precisions that are required from an alignment perspective, they are much more accurate than what flip chip bonders can reasonably deliver at a reasonable throughput. And the bonding technologies that are very well suited for that would be so-called hybrid bonding technology, which I will explain later in this presentation in more detail. We can do face-to-face bonding, basically of two wafers that have completed part of the back end of line. Yeah, and if we get down again to the other extreme, to the transistor level, then what is proposed is a semi-monolithic type integration, where actually on the first wafer, possibly only a thin layer of silicon that has not been processed yet is transferred, and then the transistors are only made after the thin silicon has been transferred onto the bonding and hybrid bonding.